I'll come by with questions if you're time.
Yeah,
I'll
if
send
you,
an email.
you're welcome. Maybe I can help you some of
Sure.
mechanics, classical mechanics.
If I don't want any answer, I just want to come to you and speak
it's
my
just
speak
up
my
to
mind. Speak my mind.
Just up to you. Yeah.
Okay.
Okay. Today we will go to this important topic. How can when we will try to introduce Lagrange, how to solve the problem, right? So first we discuss what is the difficulty in solving the mechanical problem due to the constraint, because we already introduced constraint and we know the constraint how difficult. And so now we will try to see difficulties. In solving mechanical problems due to constraint. Since we know the constraint is difficult, the difficulty in several ways, right? Let's first difficulties. First difficulty, right? Suppose we have n particles, and the coordinates for each n particle are I from R1 to Rn. Those are not independent because we have the restriction, right? So those are no longer independent. If no longer independent, so we know this is a Newtonian mechanics. We know for each individual particle, the dynamics of a linear momentum is the net force, right? So I from 1, 2 until n. Now, if these particles are not and the coordinates are not independent of each other, then you solve. We have how many equations? Has 3n, but they are not independent. Right, so you cannot solve this equation independently. That is the first difficulty. Okay, second one, due to the constraint. So we know the force of constraint is not easily to express straightforward, right? So then, okay, now that's second one. The net force. I'm going to write in terms of classify in terms of applied force and constraint, right? It's applied plus the constraint. Then this is a difficulty come. No expression, or almost not easily expression straightforward, right? If not, how can we solve this? Right? We need to write down exact force and do the force analysis, then set up equation is a vector analysis. Then we can do. But if we cannot write down this, how can we do that? So that is the most difficult, right? But here we know, or we can find the effect of the constraint from where? From the equation of constraint, right? Which we already played last time. That we know what constraint this, right? The particle is limited or restrict on the surface or on this inner surface of the sphere or on this slope, or like a simple pendulum we restrict with the length, right? So those we know. So that is these two difficulties, the major difficulty. Then now the next question, how can we overcome or solve this difficulty, right? So now, how to overcome these difficulties. That is our next job. And that is begin we think about or develop the analytical mechanics. Okay, so now first let's consider first the difficulty, and then we go to next one, right? For this one, let's see, for this, right? The first one. Now, no longer independent. Then how to deal with those if not independent? And how to do that? Okay. To solve this, let's consider the constraint because it's due to the constraint, right? Why not independent? Since we have some restriction or constraint and reduce degree freedom. So now let's consider what type of constraint we discuss. Holonomic, non-holonomic, right? So let's first consider holonomic. Constraint first. For non-holonomic, in chapter 2 we are going to extend, right? So now let's just consider, so that is condition. Just consider this. If not holonomic, then how to deal with, we will introduce this unknown, this Lagrangian multiplier. So that is some of other technique. So now let's consider this one. So if we have this, now let's suppose, right? So now we have, I'm going to say this, what is holonomic? We can always write down this, okay. Let's just use vector. But each vector has 3 components, right? Just keep in mind, in general. Right, that is the equation of constraint for holonomic, right? So alpha, how many? Suppose we have k equations. So that means we have a k equations of constraint, and that means, suppose we consist, then the degree of freedom, how much? Let me say I'm going to use lower n. So when we consider constraint, the total degree of freedom be 3n. If without constraint, right, we have n particle, each one has 3 x, y, z. So 3n minus k, right? That is the total number of degree of freedom we are going to determine. Okay, so that is the first, how much we know, how many independent variables, lower n is this. Okay, that first. Then that is the second. Once we know this, since these are not independent, now we are going to select another side of the coordinates which are independent. And then we are going to say that is generalized coordinates. So now introduce generalized, okay, coordinate. Now instead of R, I'm using QJ. So here I is defined index is represent the number of particles, right? I from 1 to n. Okay, so here I from 1 to n particles, right? Now j from 1 to lower n. How many degree of freedom? So now I use QJ, and you may say, what is QJ? Later I'm going to discuss in details. So here I use QJ, then when you look at the QJ, that is generalized coordinates. That will be introduced. So when we introduce general coordinates, then what the next step is, we are going to transfer the dynamic or equation motion for this I particle, right? And by analyzing the force to general coordinates. So that is, but before do that, since we have introduced some new terminology or new term, let me give you some details discussion about this. What is definition, what is a feature, and how to select, right? So now let's discuss the general coordinates. Okay, so generalized coordinates. First type. Okay, what is the definition of our type of
What is the symbol that you use for generalized coordinates?
Q? Sorry, it's QG, right?
Okay.
Okay. No any restriction. All sort of this quantity you can select. So that means here it can be position, which we familiar. Positions like xi, yi, ji. Yes, that is one possibility we select if it is possible, if it is good to use, right? Or angles, for example, theta, phi, and other, if you chi or alpha, beta, right? Let's say, whatever. So those angles, we can also select angles as a general coordinates, right? Then we can also like magnitude or amplitude of like a Fourier transfer. We will have so each amplitude as the general coordinate. Amplitude of amplitude in Fourier transfer. But this is those example you may ask why. No, why it really depends which one you prefer or good of Ri, right? And okay. So in general, it is even it is not required for us to be an inertial quantity. For example, energy, time, maybe is also fine. So that is an angular momentum, right? So that you just this all type and which type. Let's give you depend on the system which. Okay, then just angular momentum and then sometimes times. Okay. Time is not quantity. Yeah, sometimes time. Okay. So then once we have this, then okay. Then you need a dimension, right? Dimension. Then going to discuss. Okay, let's discuss. Yes, sorry.
How can you just represent position, a point by angles? You need the magnitude of the radius or something.
Let's see. Well, I will show you what how do we need the magnitude or not? Maybe angle enough, right? So that good question. So we just keep in mind how to. This is also a challenge, like how to write the equation of constraint. That is something new for us. This is also something new. So let me first give this type and feature, then we go to some examples. Okay. So then the dimension is different, right? Dimension depends. Right? Also depends on which you are choosing. You choose. If you choose the position is dimension is meter, right? Angle is degree, and others. Energy is a joule, right? So that dimension is be also keeping this is depends. Then we are going to have the feature. We have asked when you select, yes, fine, but you have to keep this is satisfy some feature that first okay. Since we select the general coordinates, that means has the n general coordinates, n is degree of freedom, so that's be independent, right? If dependent, that is not our goal. Since we want to transfer from dependent Ri to sub QG, which are independent, so that we have this get rid of or overcome this first difficulty, right? So that's be independent. So when you select, you have double check as it's independent. Second one must be complete. What does means complete? You select the general coordinates, and of course, if you select independent and the number of the general coordinates n, that's be complete. I mean, you have to use those general coordinates so you can determine all the position at any t time t for n particles. If you miss some of them, not complete, right? So that you have to double check your select this one to be complete. Okay, I think the others are fine. Since I already emphasized that's be under this holonomial. So once we have this, now how the next one is how to choose general coordinates. That is our next job, and I'm going to give you some example and the general step, so help you know how to select general coordinates. First, steps. So step 1, what you need to do is follow here, right? Step 1, you'll find the equation of constraint. Equation, since we have many, right, of constraint. That means when give you this, when give you the problem, you need first analyze what is the limitation of the motion, or what is the restriction, how many. So you're going to find. Then you can determine in this case. So now I'm going to write again. It's a holonomial. So what you first you write equations. This be holonomic, right? Then you are going to count how many. So you have the number k. With this, then you can determine the number of degrees, right? Degree of freedom, the term, and we determine n. Then you know how many general coordinates you are going to select, right? So that is first step. Step 2. We are going to choose n general. Okay, just use this one. Choose general coordinates qj and j from 1 to n. Since we know n, so you need try to find n qj. And then when you select qj and qj, you need double check. Are they independent? Are they complete? So both you need to double check. So suppose this is step, and then I'm going to give you an example. After this, you need, this is not finish. Once we have this, we are going to find the relation between the general coordinates and the real coordinates, right? Otherwise, the goal is we solve, this is our goal. We want to find the dynamics for this, but we cannot solve this from the equation easily, so we introduce the general coordinates. Then they solve this equation for this one, you have to go back to here, right? So that means we are going to find, write down the relation between these two, we call the transformation equation. So we are going to write down, and how to write down, that actually is not so difficult. Since when you try to find this, you also in your mind, you know how come I'm going to select this one, and depending on the constraint, right? So you have some relation to this, then you will see that. Give you an example. Write down the transformation energy. Equation. Equations. And their time derivative. Because those we need, right? And we need to solve dynamics of each coordinate, each particle, right? And their time derivatives. Okay. So that is R1. I'm going to have R1 is function Q1 until Qn, right? J from 1 to n, and time. Then they also we have, then we do the time derivative, right? Once we have R1, so we have R1 dot, which is also a function of Q1, Qn, T. Then how many? We have n, right? So we have n transformation equations. Q1, Qn, T. And then you do the derivative. Okay, so we need 3 steps. Now, I'm going to, let's do some examples, see how can we do that. Later on, when we deal with the problem, we always have this step. So let me just give you 2 examples, and later you can do it yourself if you follow this scheme, and also we can do it together, right? So examples. Let's first example is a particle moving in the inner surface of sphere, which we already have this equational constraint. So now let's say a particle moving on the inner surface of a sphere. So we have this one before. This R, right? So this is a particle here, X, Y, Z. Only one particle in this case. Okay. Now, first write down. So now let's first write down or find the equation of constraint, right? So equation of constraint is F, X, Y, Z is, because whatever you go, X squared, Y squared plus Z squared always equal to R squared, right? Because they always move on the surface. So that the constraint is X squared plus Y squared plus Z squared minus R squared equal to 0, or I just directly use R squared minus lower R squared minus capital R squared equal to 0, right? So how many alpha equal to 1? Or so that means K equal to 1, right? Only 1. This is R, right?
So basically here what you're doing is you're doing some kind of dimensionality reduction, right?
Yes.
That's what you're doing.
Yes. We introduce general coordinate because we know the n coordinates, 3n coordinates are not independent, right? Mm-hmm. So we are going to select the independent.
It's like changing the basis.
Kind of, but not same dimension. For example, here is 3 dimension, but you change to the 2 dimension, since you will see only 2 degree freedoms 2, right? Yeah, kind of, yes. You that means you from the R to Ri to JQ. Yes. Okay, so now we are going to first step. You need to find the general coordinates and you determine how many K. How many general coordinates. So in the equation states, in this case, only 1, right? Now, so n equal to, now we are going to determine the degree of freedom, lower n. How many? 3 n minus k, right? Let me use the formula here. In this case, 3 multiply capital N, only 1 particle, right? Minus k, k is 1, so how many? 2. So we only need the 2 degree freedom which are independent. That means we are going to select the general coordinates, we need 2. Okay, so now we are going to go to here. We're going to choose Q, J, and J from 1 to 2, right? How to do that? Which one you are going to select? That is use our knowledge, right? So now, let's consider. So if in any case I have an angle here, right? And then for each position I can have a plane circle, and with this circle I can have to distinguish this particle right? So this is 2. Okay, let's see. They are independent, right? First, yes. Whatever theta change, phi will not change, or I mean not dependent. So that they are independent, complete, yes, because they need only 2 and this 2, yes, complete. Okay, now next one is, so we are going to select Q1, for example, theta Q2 is phi. That is step 2. And you may ask why you select this. That is based on our knowledge, right? So we will know this one can characterize the general coordinate properties. Now, number 3. So now we are going to find transformation equation. That means find the relation between R and Q, or Ri Qj, right? So very easy. Let's consider. Let me use this space. So now transformation equations. X, right? X is first R project to this green and then project to cosine, right? So I think if I write down, you're going to forget it. This is capital R sine theta cosine psi, right? And similarly, Y is R sine theta sine phi, and Z is R cosine theta. So you see, this is not so difficult. Once we set up the general coordinate, because when you select general coordinate, you also have some idea relation between the coordinates and the general coordinates. So you can write down, try to find, once you define this general coordinates, you're going to find how to determine the x, y, z in terms of general coordinates, right? That answers your question. Okay, so you see here, R is a fixed. It's constant. Yes, it is radial, but it's a constant. It will not involve in the equation of motion. Only this theta phi. So now, as I said, once we have the transformation equation, we also need immediate, because later you will see we need this in the Lagrange in the kinetic energy. So here you just immediately write down here. So you do this. Okay, you do this because this theta and phi as a function of time, right? So when you do the derivative, you do this one and keep this one, and then keep this one to this one, right? Okay. It's R, for example. Let me see. Keep this to this, so I have a cosine theta dot, and cosine phi, and plus R. Actually, it's minus, right? Because this cosine to is minus, right? So R sine theta sine phi and phi dot. That is x dot and y dot. Similarly, R cosine theta dot sine phi and plus R sine theta cosine phi dot. Z dot is minus R sine theta dot. Okay, that is the 3 steps. And then later we are going to use those into the equation. That is the next important job we will introduce the Lagrange equation. But let's step by step. So this is example 1. Any question for the example 1? Okay. Now let's go to next example. Is we have a double pendulum on the vertical plane. Also a double pendulum vertical plane. And the picture is like, so we have a vertical. We have here the first pendulum here is M1, L1, and the second one, L2, and 2, right? So I have X, X1, Y1, X2, Y2. Two pendulum or two particles, the position we have to calculate by X1, Y1, X2, Y2, right? Okay, now, so for this one first, again, we first find the equation of constraint. Let's analyze the constraint in this case. We already did before, last case, right? If you remember, we have two, right? Because this constraint and this constraint actually have two. So now let's write down. The first one is x1 square plus y1 square minus l1 square equal to 0, right? So that is alpha equal to 1. That makes sense? Second one is x2 minus x1 square plus y2 minus y1 square minus l2 square equal to 0. So, do you remember this? And how to write this is straightforward. You can see, you can find this. So that the right equation of constraint is not so difficult. Let's say the effect of constraint on the motion is not difficult to express, but the force is difficult. Okay, so now how many? The k is 2, right? We have two equations of the constraint and they are holonomic. First, double check. Those are holonomic, so I didn't write down here. This is also holonomic, right? Okay. Step 1. And then we can determine, step not finished. Now we determine n. N, okay. Now, I'm going to write down 2m minus k if you agree. Because we just, this actually, if you say that 3n, then there's another constraint that if you're not, the z direction is 0. Right? So you have more constraint if you want. Or you just reduce this dimension from 3 to 2. That makes sense here?
Yeah.
Okay. So this one is up to you. It's actually, this implies z1 equal to 0 and z2 equal to 0. So in that case, you have 4. K have 4. Then this is 3, right? If you select 2, we ignore those. That makes sense?
Yeah, that is also a constraint.
Yes. Okay. So it really depends. I just put here. If you consider 3D, 3 dimension, you have also another constraint for this 2. If not, you just consider 2 dimension, that's 2, right? Okay. Then here. Now, number of particles, 2 particles, right? So n is 2. And k is 2. So how many? 4 is 2. So the degree of freedom in this case, we need to find 2 independent. Now I'm going to independent general coordinates. So which 2 you are going to select? We have 4 variables, x1, y1, x2, y2, but actually among these 4, only 2 are independent. So we are going to select 2 such that we can express those 4 variables in terms of these 2 general coordinates, right? So when you select, you think about they are independent. Okay, let me use. So now I'm going to
2 angles.
yes, 2 angles. Theta 1, theta 2. Okay, so now choose the general coordinates. So Q1, I'm going to select theta 1, and Q2, select theta 2. And they are independent, obviously, right? So yes, make sure. And also they complete because it's only need 2, so yes, we have 2. All right, so that is, once we define that, you have then the transformation equation. Okay, transformation equation, let's x1, very easy, right? x1 is cosine, the L1 cosine theta 1, right? So L1 cosine theta 1 and y1 is L1 sine theta 1. Y2, x2 first. x2, this is x1, okay, let me see. X and y, right? So this is x1. x2 is x1 plus this part, right? This is x1, right? Because it's vertical, right? So this part is this triangle one part, right? So then that means it is x1 is this one L1 oh, we use sine, right? Not cosine. sine theta 1 and plus, okay, L2 sine theta 2. So you can see here, I only need theta 1, theta 2. I can express these four quantity or variables. L1 cosine theta 1 plus L2 cosine theta 2. Then you can do the derivative. L1 dot is L1 cosine theta 1 dot, and Y1 dot is minus L1 sine theta 1 dot. Then the X2 dot is L1 cosine theta 1 dot plus L2 cosine theta 2 dot. Y2 dot is minus L1 sine theta 1 dot minus L2 sine theta 2 dot. All right. So I just show these two examples, and later, either from homework or from the later we have some other examples. You can see the other how to select these general coordinates. Okay, this is how we solve the first difficulties.
Excuse me, Prof.
Yes.
So why are we exactly doing this? Because if we already know the equation of constraints, then we can replace the dependent variables with the independent variables and do it directly, right?
Yes. For example, if you know this,
Yeah.
but how to replace? You need to go to the here. You need to find this.
No, we can write z as a function of r, x, and y and replace that in the original equation.
This one, right?
Yeah.
Yeah. But from here, how to replace x?
X is equal to root of r squared minus y squared minus.
Oh, okay. Then you still not solve.
Huh?
If you use x squared equal to r squared minus y squared z squared, right? Those are dependent. You still not solve the problem that you are going to find independent variables.
Now y and z are independent variables.
Oh, okay. Yes, good question. You can do that way, but later you will see this is not a good way. When you solve the problem, you will see it is not make your equation is simple or easier to solve. Yes, you are right. That is, I want to mention that, but I forgot to remind me. Yes, it does not mean this is unique. You can select any arbitrary two independent variables, like yeah, she said, I'm going to select y and z. Yes, you can. And then x is that, and then y and z as in the, but then later you will see in when we derive this general coordinate, I mean the Lagrange equation, you will see this is not convenient. Okay. All right, good question. Now let's go to the second difficulty, which is really difficult, and we are going to how to solve. So I'm not sure it's 2 for difficulties equation of motion. That is due to this constant force, right? So here, Pi dt equal to Fi applied plus Fi constraint. So here, this is a difficulty, right? Come from. How to do that? Okay. We know we cannot ignore the force. So we cannot say, okay, let's drop this one, just solve this one. No. We know it's very important, right, to limit the motion of the part or system. So what we have to do is, if we cannot get rid of this one, how? Let's just think about alternately. If this is a force, how about the force, the work done by this force? If it's 0, then we are going to, instead of to look this vertical equation, we are going to look this the work, right? So how about the d? I'm going to use I infinitesimal is w work done by the here, okay, constraint. So now we are going to look this term. That is introduce the principle of virtual work, and we will see from that principle, and if we make some of approximation that makes sense or that acceptable. So that is the idea. We are turn our way of thinking to another way to try to find the alternate way, try to solve this problem, right? Not straightforward to overcome this one, but try to see how to do that. How to do that? First, we introduce what is one. So, okay, this is a virtual infinitesimal, virtual displacement. Virtual displacement. What this means? Virtual displacement is infinitesimal change or this change of the coordinates, right? So that is infinitesimal change of displacement. That is we define. Okay. Or coordinates, I can say. Coordinates. Okay. Then this is not equal to delta r. I just gave you this is real displacement, even though maybe this is infinitesimal small, but this change will after this change is depend on delta t. So that is associated with delta t here. No change time. Just a time t we consider virtually if there's a displacement. So that is the difference. Now, when we consider this, so now let's look the work done by the total force. And in particular, there are two parts, right? Then we will see. So now we are going to consider the work. By let me go to net and delta r means virtual displacement. Let's look this. So first, let's consider as equilibrium, and then we are going to introduce or consider general, right? At equilibrium, at time t. We know the net force, if equilibrium net force is 0, right? If not equilibrium the force, then will drive the particle move, right? But if the force is 0, the net force here, right? So that is at this one. Then we are going to look this. The virtual work overdone by this we call the virtual work. Then we call the virtual work, right? Work means the work done by the force under this virtual displacement, virtual work. Okay, dWi is equal to that's equal to 0 because this one is 0, right? No work done, since no force, right? Yes, that makes sense. If this one, then the total virtual work, we have n particle, right? So it will be sum of all, to be I from 1 to n dWi. That means I from 1 to n, each particle has a net force, delta R1. That's equal to 0. And that just makes sense, we know this. So that is if at equilibrium, because the total net force is 0, so that is also 0. Then here we want to Now the total force or net force on each particle include, we are classified force in terms of applied force and constraint. Since here we want to get rid of this one, so we're going to use this, right? So that is applied net applied plus the total, so I'm going to say constraint means all the constraint associated. Okay. So if we substitute this total net force into this one, then we have two terms. So we have the summation I from 1 to n Fi net dot delta Ri is equal to two terms. One is the applied force. Do the work, do the virtual work. Another is the force of constraint do the virtual work, right? And that's equal to 0 by here, since the net force is equal to 0, so that's be 0. And now we're going to restrict. So here, again, still have this problem, but this one, in most case, this the force constraint always perpendicular to the virtual displacement. So that's be 0. Most cases 0. So then we can do this restriction. Now, even though we will not prove always equal to 0, but let's just restrict our system such that the work done by the constraint force is 0 or always perpendicular to the virtual displacement. Okay. Restrict is this one. Summation constraint just means second term we just restrict or remove this one. So here is it is good assumption for most cases. Example, let's consider we have we have the surface particle moved at the surface, right? And we have R and move, for example, the delta I. And what is this constraint, the force? It's the limit of restrict motion on surface, so that means that is, yes, that is perpendicular to the this, right? So that is, even though we do not know how to express, but now we know this is a normal force. So, but at least we know the direction. In this case, right? So that means because this is, for example, constraint perpendicular to the delta Ri. So we have this constraint, this work done constraint perpendicular to equal to 0 in the product. So that, yes, that this one. Let me just do another second example, and the others I think I just have the pendulum, a simple pendulum here. And we have L here. So what is constraint here? It will not, the particle will not move along this radial direction, right? So the force or the force constraint is from tension. That is this one. And this one is delta RI. Same thing. And you will see most case is satisfied. So we do this approximation. If
But-
not, yes.
But like friction, for example, that is not
Yeah.
true, right? So,
Fraction, yes, no. Yeah. Fraction, actually, later we do have example. The fraction, there are some other force we can express, then we can go to absorb into the Lagrange equation. Okay, yeah, later we will do that. So, yes. Okay, so then the conclusion here. With this, now we have a conclusion which is a principle of virtual work. So now we have a principle of virtual work. Is sum over all the particle from 1 to n, all the applied force do the virtual work equal to 0. Because this term equal to 0, right? We restrict that equal, so then this result come to here. So that is important result from here. Now this is applied force. And all the applied force do the work on this, virtual work on the solar system somehow together. So here, please keep in mind that each individual net force of applied force is not 0. Force not 0. Only somehow all together the work done by those together is 0. That is only. So that is first, even summation of all the net force, applied net force also not 0. There exists. But right, only the summation of work, right? So that is inner product of applied force to the virtual displacement, not 0.
It is not equal to.
Sorry?
Second would not equal
Second one.
to. You put equal to 0.
Okay, yes, you're right. All right. So that is the result. Now you may ask question. Yeah, that is as equivalent. I can acceptable that because the total force 0.
so this is when there is an equilibrium.
This is at
At
equilibrium.
equilibrium.
Then we are going to now we are going to discuss non-equilibrium.
Also, one more question was there can be an equilibrium where the particle is moving about its mean position, dynamic.
Dynamic, we said equilibrium at any instantaneous time t. So that case is not equilibrium, right? That is we are going to discuss. Okay, so now this is right. So now I'm going to say it's like a separate at non-equilibrium. At any time. So this is non-zero. How to do that? And that is what we are going to solve the equation of motion, right? So now that means we follow this from the Newtonian equation. The total time derivative of the linear momentum for each individual particle equal to the net force on the particle. The net force is not 0. And now I'm going to rewrite this one in term here. This is nothing but a P dot, right? And then I'm going to move this one to the left-hand side. So that means Fi to the right-hand side. This one is included applied and constraint, right? Minus Pi dot equal to 0. So if I do this way, you can see right-hand side 0, then we can define that together is another total force, but then we just introduce the terminology. This is the reverse active force. Reversed effective force. because in the dimension it is false, right? Dynamic, the P dot, its dimension is Newton. And now, since it's Newton, so we give a name, it is a reverse effective force. It is not real force, but it's kind of force. Then we consider the system total net force subtract the reverse effective force, that's be 0. Then we can consider that as equilibrium, right? Okay, then we are going to apply. Now apply the principle of force work. Is here. This is a final, but that means since this together is 0, right? So then we have sum of O from 1 to n. Now the force, each s particle has net force, and subtract this reverse effective force, Pi dot, do the virtual work equal to 0. Because this is 0, right? This 0 multiply anything is 0. So that works. The only difference now we have another term. Previously, the net force is 0 at any instantaneous time t, then that's 0 because 0 multiply anything 0. Now we subtract this one, so this is 0, right? From there. So, yes. Then we go to next. We are going to analyze this formula or this relation, what the information gave us. So now I'm going to extend this one in term apply the constraint, right? So now that's equal to, and keep continue. Here apply. Applied force, net applied force, minus Pi dot, inner product Ri, and plus another is only the work done, virtual work done by this constraint force. Constraint. Right, that's equivalent. Then we do the same thing because this restriction also apply in any case, either equivalent or non-equivalent, right? So we restrict. All this virtual work done by the constraint force, we can ignore, or that's in most cases 0. Then we're down to here. So you will see we have this the equation which we call as this is from the equilibrium. We call this principle of virtual work. For non-equilibrium, we call this is the Allenberg principle. So now we have this sum over all the particle from 1 to n, but only the applied force, right? I net applied minus the reverse effective force Pi dot to the virtual displacement equal to 0. So this we call the D. This D. Allenberg principle. Or differential principle. Later, chapter 2, we're going to introduce integral principle, which is Hamilton's principle. So sometimes people say differential equation, principle, or the Allenberg principle. So now you can see we deal with the applied force and this the Pi dot. Then no any constraint force here. So we get rid of, but does not mean there's no constraint force. Constraint force still exists, right? So now I'm going to give you, so now we are going to what's study or discuss what kind of information we can extract from here. Information can be extracted from it. This we are going to discuss. Okay, in order to do that, we need go step by step, so then you can see this information. First, okay. All these constraint false. Okay. That no longer appear, right? That is good. So difficulty we can appear, right? But the effect, they did not ignore the effect. The effect is very important. The effect of the constraint false effects are taken into account from their equation of constraint. We introduce general coordinates, right?
Yeah.
From account from the equations of constraint, and that is important. That is all are from here. From 1 to k. So that means instead of to solve the force, to analyze the constraint force, we are going to apply the equation of constraint. And due to, through that one, we are going to introduce general coordinates. Then we are going to find what is the equation of general coordinates that start or transfer from the Newtonian equation to that, right? Transfer from here to that. So that is the first information keep in mind. Okay. Second one. Keep in mind, even though this is the virtual displacement here, they are not independent, right? Because the constraint. So, not independent. What that means? If not independent, that means they are linear dependent. So this term is not zero, right? If this is independent, then that means all the coefficients be zero. Then your set is zero, but it is not, right? So that means this applied, it does not mean they are equal to zero. That is the second information you keep in mind. We just try to convert this the constraint information to the equations constraint, and then we're going to deal with this by introducing like general coordinates, right? That is the next step. That's why we introduce generalized coordinates. So here for I from 1 to n, they are not okay. Then, as we discussed, to overcome this first difficulty, we introduce the general coordinates, right? So then we can number 3. So we for if this holonomic constraint, we introduce general coordinates. And here is j from 1 to n, and where n is 3n minus k, right? So that is we just play. Then with this, we have a transformation equation. That means here, this equation delta Ri. How to find delta Ri? Because they are independent. They are not independent, they're dependent. So we are going to replace in terms of general coordinates such that they are independent. Then you need to find the relation between Ri and Qj. That is transformation equation, right? So from transformation equation. Now I'm say when I say Qj means Q1 to until Qn, right? So I just make simple. I from 1 to n, j from 1 to lower n, right? So once we have this, now we are going to find from here. Our goal is to try to replace this one by that is our goal. How to do that? We need to first find how to express this one, how to try to find this one, right? Okay, from here. So you can see here, Ri is a function of Qj and time. Now we are going to play that little bit. So the total time derivative of Ri with respect to time, this du is total, not partial, right? But since it's a function of those variables, so that be all the partial variable we have to consider that. I think you all know, right? Mathematically. So that, if I use R dot, is this one, right? That is total time derivative, and that's be summation from let me see, j from 1 to n, because we have a q, how many qj we have a n, right? So that is lower here. That is lower n. That is for the index for the general coordinates, and partial I, partial qj, and partial qj, partial t, right? Is that finished?
Yeah.
Yes or no?
Yeah. D.
We have another one, right? Careful. Okay, so here this one is nothing but this is qj dot. So now I'm going to rewrite this one. J from 1 to lower n, partial Ri, partial qj, qj dot, plus partial Ri, partial t. Okay, this is a total time derivative, and we have not come to here. Later when I'm going to do that. So now this is R dot, right? So now you can see another one. Now R dot is also function. I'm going to say you can see also function R dot of qj and t. Not only qj but also qj dot and t. Do you agree? So here Ri is a function qj and t, but here we have a qj dot. So Ri dot is function of qj general coordinate, general velocity, and time. Okay, so that is also the function of all the variables. Then let's do partial Ri dot, partial qk dot. You will find a very important relation. So now let's do that. Ri dot here, right? So now I'm going to say there's a partial, since partial, and just direct it to this, j from 1 to n, partial Ri, partial qj, and then dot is only this one, because qj and qj dot, they are independent. So only this one is function qj dot, right? This Ri does not depend on qj dot. So here I keep R, and then this is a partial qj dot, partial qk dot, right? This one does not depend on qj dot, qk dot, right? So that is, then you can see here, because they are independent, this means when only k or j equal to k is equal to 1, otherwise equal to 0, right? So that means it is j from 1 to n, partial Ri, partial qj, delta jk. Only when k equal to, j equal to k, right? Then you have all summations, so that means Ri, partial qk. Then you can see right hand side is partial Ri dot with partial qk dot. That equal to partial Ri, partial qk. So this relation is important when later we derive the Lagrange equation or another case later. You will see this is very important. We can replace this. Okay, once we have, now we can find what is delta Ri. Then we are going to substitute delta Ri into this equation. The goal is try to remove those dependent variables by independent variables, right? So now d Ri is partial. So that is j from 1 to n partial Ri partial q j delta qj, right? Plus partial Ri partial t delta t. That is total difference. This is the total differential, right? This is partial differential only with respect to the space. This is also another partial differential with respect to time. So here, this one is the virtual displacement. Only depend time, space, right? So now the virtual displacement is only with time, instantaneous time, no time change, but only this displacement. So that is the relation here we find partial Ri partial Qj delta Qj. Okay, I already erased the formula here, right? So the Eilenberg equation.
Professor, could you repeat that?
Okay, sorry?
Could you repeat that step from this?
Say again?
Could you repeat that?
Okay, I repeat. This is total differential, right? Okay, total difference because the function is function Qj and time. So then the total change with space or general coordinate and with time. So these two are partial differential, right? One is only space, another time. But we define this delta R as virtual displacement is only the space.
Yeah.
So that is delta Ri is the first term.
Okay, so we put that one 0.
No, not 0. This is a total definition. If you consider total change, you have these two terms. But if we only consider, this is our definition of virtual displacement, is only this space. So that is the first term. Okay, yeah. All right, so with this, now we can have this, go back to, okay, I think, let's look at the first term. Let's look this. Remember, just the first, we have applied minus pi dot, right? This one. And now we're going to have the first term. So that is a first term, second term. Let's do one by one. We cannot finish the whole, but let's first start from the first one. So let's look the first term. A summation for I from 1 to n, capital N. The applied force is delta Ri. This term. Okay, since we have the delta Ri, so we just substitute here. That equal to summation I from 1 to n. I go to this force, applied force. Now delta I is Ri is this summation, so we have summation j from 1 to lower n partial Ri partial Qj delta Qj, right? That is delta Ri. Then I'm going to, since we are interested in the independent, then I'm going to take this summation outside. Change the position, right? Change the summation. The first is n j from 1 to n, and then this all are dependent on I, right? So now inside is I from 1 to capital N, I night, applied force. Inner product here. This inner product, right? So there's dot here. Partial Ri, partial Qg. And then outside delta Qg. So that means this, since delta Qg are independent, so those are the terms. Of course, these are not zero since we have another term, right? We have second term. But now we are going to deal with this one. And this one, we are going to introduce by another new term, or name, capital Qg, delta Qg. So capital Qg is defined summation for all the particle. It's applied force. Is inner product of a partial Ri with partial Qg. So Gf from 1 to lower n. Now, this is a new term. And this term is this inner product of these two. We give a name, that is generalized force. Qg, give a name, generalized force. Okay, its components, okay, G's components. G's component of general force. How many? We have lower n, right? G, depend on G. So these components, we have the lower n components of a general force. And the definition here, right? That is definition. Then here you will see the definition of this force. Did I discuss this? I think I discussed this unit. What's the time? Okay, let me stop here and I'm going to explain. You will see this one is, the dimension is not force, not Newton itself. Depending on what type of your general coordinates. It may be force, it may be torque, it may be some others, right? So next Tuesday I'm going to discuss this. All right. And then we'll have another class, so I don't want to occupy time here. I got your email, right? Send me the paper. Yeah, I will look that.
Yeah.
And I think I have some idea already, but I'm going to see what they are talking, and then we can discuss it.
In next week, I guess.
Yeah, next week sometimes, maybe in the class or after class. If it's important concept, I would like to discuss in a class. Yeah.
I need the middle part.
Okay, I just leave here.